What if I told you there's a fundamental limit to what we can ever know about the universe? Seriously, that at the tiniest, most fundamental level, reality itself has a built-in fuzziness where perfect, absolute knowledge is literally impossible. Now, this isn't some philosophical debate, it's a cornerstone of modern physics, and it completely turned our picture of reality on its head.
Okay, so let's get right into it. Back in 1927, a German physicist named Werner Heisenburg discovered this mind-bending truth, which we now call the uncertainty principle. The core idea is this: it's impossible to know both the exact position and the exact momentum, which is just mass times velocity, of something like an electron at the same time. You can know its precise location, like a pin on a map, or you can know exactly where it's headed and how fast, but you can never, ever know both with perfect certainty.
So here's our game plan for unpacking this whole idea. First, we'll look at the actual math behind it. Then, we'll dive into how just looking at something can change it. We'll figure out why this weirdness only really matters in the microscopic world, see how it completely upended old ideas about the atom, and then we'll wrap it all up with the key takeaways.
All right, first up, the mathematics. Now don't worry, it might look a little intense, but it's actually a pretty elegant way of capturing this fundamental rule of the universe.
Okay, let's break down this equation. That little triangle symbol, that's the Greek letter delta, and in physics it just means the uncertainty in something. So delta x is the uncertainty in position, the where is it part. And delta p is the uncertainty in momentum, the where's it going part. The equation tells us that when you multiply these two uncertainties together, the result has to be greater than or equal to a very specific, incredibly tiny number. That number involves something called Planck's constant, h, which is kind of like the universe's smallest possible unit of anything. But here's the kicker: because that number isn't zero, the total uncertainty can never be zero. The universe itself enforces a minimum amount of fuzziness.
And this is a fantastic way to visualize the trade-off. Think of it like a cosmic seesaw. Let's say we push down really hard on one side to get super high accuracy on the particle's position. That means we make delta x really, really small. Well, what happens on a seesaw? The other side has to fly way up, right? And that's exactly what happens to the uncertainty in its velocity. Or, if we do the opposite and nail down the velocity perfectly, its position becomes incredibly blurry. You just can't have both sides of the seesaw down at the same time.
Okay, so if the math wasn't weird enough, let's build on that, because it leads to an even stranger idea. It turns out that at the quantum level, you can't just be a passive observer. The very act of looking at something changes what you see. So think about it. How do you see something as tiny as an electron? Well, you have to hit it with something, usually a particle of light, which is called a photon. This diagram shows exactly how that plays out. In step 1, we send a photon toward the electron. Step 2, wham, they collide. In that instant, we've registered the electron's position. But look at step 3. That collision has sent the electron careening off in a totally new direction with a new speed. So the act of measuring its position has completely changed its momentum. We know where it was, but now we have way less of a clue about where it's going. Now, I know what you're probably thinking. This all sounds, well, completely bizarre, right? So why don't we see this in our everyday lives? I mean, a police officer can clock a car's speed and know its location at the same time. What gives?
Well, it all just boils down to a question of scale. Here's the thing. The uncertainty principle is always true. It applies to everything, from you and me, to a golf ball, to an atom. But for big, macroscopic objects, the effect is so unbelievably infinitesimally small that it's just completely impossible to measure. It only becomes the undeniable rule of the game when you shrink down to the microscopic world of atoms and electrons.
Let's actually put some numbers on this. Take a regular 40-gram golf ball, flying at about 45 meters per second. Now let's say we measure its speed with a pretty good accuracy of about 2%. That gives us an uncertainty in its velocity of 0.9 meters per second. So what happens when we plug all that into Heisenberg's equation to find the uncertainty in its position?
The result is this: about 1.46 times 10 to the power of negative 33 meters. I mean, that number is so ridiculously small, it's basically meaningless. It is trillions of times smaller than a single proton. So for all practical purposes, in our big world, the uncertainty is zero.
Okay, but now let's do the exact same thing for an electron. Its mass is absolutely minuscule. Let's say we want to pin down its location to within 10 to the negative 8 meters, which is roughly the size of a small atom. What happens to the uncertainty in its velocity?
Well, the result is just staggering. The uncertainty in the electron's velocity explodes to about 10,000 meters per second. That's incredible. By knowing its position pretty well, its velocity becomes wildly unpredictable. So the bottom line is, at the quantum scale, this uncertainty isn't just a tiny footnote. It is a massive, defining feature of reality itself.
And this principle wasn't just some quirky little problem for physicists to solve. It was a full-blown crisis that shattered the old, comfortable clockwork view of the universe. It forced them to create an entirely new way of thinking, quantum mechanics. So this leads us to a really deep and profound question. If you can never know exactly where something is and also exactly where it's going at the very same instant, what on earth does that mean for its path?
It means the whole concept of a trajectory, as we normally think of it, just gets thrown out the window for an electron. I mean, to plot out a path, you need to know the location and the velocity at every single moment. But since the uncertainty principle forbids that, the idea of an electron following a nice, clean, predictable arc is just fundamentally impossible.
And that, right there, is exactly why the older models of the atom, like the famous Bohr model, were doomed to fail. You've probably seen it. It pictures electrons zipping around the nucleus in neat little orbits, like planets around the sun. But a defined orbit requires a defined position and a defined velocity at all times. And as we now know, that's a direct violation of the Heisenburg uncertainty principle. It just couldn't be right.
So physics had to have a revolution. Scientists had to completely let go of the idea of certainty. The big paradigm shift was to replace precise statements with statements of probability. We can no longer say an electron is at a specific point. Instead, all we can do is describe a region of space, what we call an electron cloud or an orbital, and then calculate the probability of finding the electron somewhere inside it. And this isn't some kind of downgrade. This probabilistic view is the bedrock of our modern world, from the chips in your computer to the future of quantum computing.
All right, we have covered a ton of ground here, so let's just take a moment to boil it all down and summarize the absolute key points from all this.
So let's put a bow on this. First, you've got the formula, the universe's fundamental rule that total uncertainty can't ever be zero. Second, that rule creates an inverse relationship, our cosmic seesaw. Get precise with position, and momentum gets fuzzy, and vice versa. Third, scale is absolutely everything. The effect is totally negligible for a big object like a golf ball, but it completely defines the reality of a tiny object like an electron. And finally, the huge consequence of it all. It demolished the old idea of fixed paths and forced science to embrace a new world built on probability, giving birth to the entire field of quantum mechanics as we know it today.
The uncertainty principle really showed us that at its very core, the universe isn't some perfectly sharp, clear photograph. It's more like a beautiful probabilistic blur. It puts a hard limit on what we can ever know. And that leaves us with one last big thought to chew on. If there's a fundamental limit on what we can know, what other impossible truths about our universe are still out there, just waiting to be discovered?